Okay, guys, chapter 7, here we go. Section 1, oblique triangles and the law of sines. In this first section, we're going to be solving triangles. Remember, to solve a triangle means to find all of the side lanes and all of the angle measures. In earlier studies in our class, we solved right triangles. Now, in this chapter, we start looking at oblique triangles. Now, an oblique triangle is any triangle that is not a right triangle. Okay, in order to solve these oblique triangles, we're going to need something called the law of sines. The law of sines is a very, very popular law that we're going to be using, a popular rule that we'll be using to solve these oblique triangles. To get this started, let's start with a triangle that is not a right triangle. Now listen, if a triangle is not a right triangle, that means it's either an acute triangle or an obtuse triangle. Okay, I've started with an acute triangle here. That means all of the angles within this triangle are acute. And what I would like to draw first for you is the perpendicular from B to side AC. All right, so something like this, folks. Now it's going to meet side AC at a right angle, okay? And let's call the point at which it reaches or hits AC, let's call that D, okay? So this is D right there, okay? One thing I forgot to mention in the very beginning, which I can still mention now, is that remember that in earlier studies we talked about how side A is opposite angle A. Side B, which I didn't label here, but this is side B, is opposite angle B. And then side C is opposite angle C. All right, everybody. Right here, notice that I labeled the height of this triangle H. Okay, what I would like for you to look at is right triangle ADB. ADB, right triangle ADB. And notice that sine of angle A, remember that sine is opposite over hypotenuse. So it would be H, that's an H, over the hypotenuse, which would be C. Now, can you go to this other right triangle BDC? And this time around, I want you to consider what is sine of angle C, Remember that the sine, again, is opposite over hypotenuse. So in this case, it would be H over, what do we have for the hypotenuse? A, correct? Now, what I would invite you to do is to solve each one of these for the height. Solve each one of these equations for H. All right, this is what we get. If we multiply both sides by C, then you're going to get H is equal to C times sine of A. Over here, when you multiply both sides by A, you get H isolated, and you get H is equal to A times sine of C. Now, H is the height of this triangle. So if H is equal to this product and H is equal to this product, then we can equate these two expressions. C times sine of A must be equal to A times sine of C. Cool. What I would invite you to do next is to divide both sides by A times C. So if we divide both sides by AC, you can see that this C and that C divide out, and this A and that A divides out. And watch what we have. We have sine of angle A is to side A what sine of angle C is to side C. We have a proportion. Now, in a similar way, we can construct, a perpendicular line from other vertices as well. In the very beginning, we constructed a perpendicular from vertex B, but we can do it from other vertices to show the following. So we can say the following. We can extend it to say that sine of A over side A is equivalent to sine of angle B over side B, which is equivalent to sine of angle C over side C. Basically, what the law of sines is saying is that the ratio of the sine of any angle to the side opposite that angle is constant. Should we say that again? The sine of any angle, the ratio of the sine of any angle to the side opposite that angle is constant. This can also be extended to say that A is to sine A, so the reciprocal relationship, what B is to sine B, what C is to sine C, right? Don't forget, capital letters are used for angles and lowercase letters are used for side lengths. So this is proportional, right? The law of sine says that the lengths of the sides in a triangle are proportional to the sines of the measures of the angles opposite them. Okay? So you have both the law of sines in two different alternative forms, right? In two different alternative forms, and you also have it in words as well. All right? So this is the law that we're going to be using to solve our oblique triangles. Okay, guys, we're ready to tackle our first problem. Solve triangle ABC if angle A is 28.8 degrees, angle C is 102.6 degrees, and side C is 25.3 inches. So we're going to have to find each angle measure, which is basically find angle B, right? Angle B is the only angle that is unknown. And then find sides A and B, okay? Notice that you have 3 significant digits here. So that's what we'll be using. Notice that the angles are given in decimal degrees and the side lengths are given in decimal inches. I think it's always super useful to sketch a little diagram of what's happening and what's given in the problem, okay? All right, guys, I'm going to use the law of sines, and I'm going to try my very best to use only what's given to me. I have angle C and side C given to me, and I have angle A given to me. So what I'm going to look for first is side A. Now, because side A is unknown, I'm going to put that in the numerator of my law of sines. So A is to sine of angle A, what side C is to sine of angle C. Now, this is the law of sines, and there's only one unknown in this proportion. Side C is given, angle C is given, angle A is given, side A is the only thing that's unknown. If I multiply both sides by sine of A, sine of angle A, then I'll get A is equal to C times sine of angle A. And then divided by, of course, sine of angle C. Okay, so then I'm going to get that A is equal to 25.3 inches times sine of angle A, which is 28.8 degrees, and then all of this divided by sine of angle C, which is 102.6 degrees. Hey guys, make sure your calculator is in degree mode. All right, I'm going to punch all of this into my calculator, and I'm going to round to 3 significant digits. Okay, I hope you agree with me that we get A is equal to 12.5 inches. All right, cool. So then the other unknowns are side B and angle B. So the next thing I'm going to work on finding is angle B. Angle B should not be very hard to find because angles A and C are already given. And we know that the sum of 3 angles within any triangle must be 180 degrees. So what I can do is I can say that, angle A plus angle B plus angle C must be 180 degrees, right? We know that for sure. That is to say that angle B, which is unknown, will be equal to 180 degrees minus angle A minus angle C. So then B is equal to 180 degrees minus 28.8 degrees minus 102.6 degrees, right? So then that wasn't too bad. Then angle B then is 48.6 degrees. I did not even need a trig function at all or the law of sines to find angle B. Now that angle B is known, what is missing now is side B. So I'm going to use the law of sines here to find the last unknown. I'm going to say that side B is to sine of angle B what side C is to sine of angle C. I know that we also have angle A and side A now, but that was derived information. At least side A was derived. So I want to use as much given information as possible. So that's why you see me using C and sine C. Okay, so then we know for sure that side B then will be equal to C times sine of angle B divided by sine of angle C. That is to say, B will be equal to 25.3 inches times sine of 48.6 degrees over sine of 102.6 degrees, okay? I don't mean to have 3 decimal points there. Here, let me fix that for you. Do you see the 3 different decimal points there? Didn't mean to do that. So 102.6 degrees with 1 decimal. All right, cool. So then when you punch all this into the calculator and you round to 3 significant digits, you get that B, side B, is 19.4 inches. Don't forget your units, okay? Inches. All right, there's one thing I want you to notice. We brought this point up when we were face-to-face in class, but I want to bring it up again here. These are our answers. Some of them were given information and others were derived. I want you to notice the largest angle is opposite the largest side. The middle valued angle is opposite the middle valued side. The smallest angle is opposite the smallest side. So that tells me that, it gives me a strong clue that my calculations are correct. So look for that kind of matching there, correspondence when you are done with your problems. All right, cool. Let's go to the next example. Check out this problem. An engineer wishes to measure the distance across a river. She determines that angle C is 117.2 degrees, angle A is 28.8 degrees, and B is 75.6 feet. Find the distance A. Don't mind my very fancy drawing. I have a river and I have an oblique triangle. It's actually an obtuse triangle because angle C is obtuse, more than 90 degrees. All right, so in order to find side A, which is your unknown, we're going to set up the law of sines with A in the numerator. Okay, so we have A is to sine of angle A, what B is to sine of angle B. When we multiply both sides by sine of A, we get that A is, which is the distance across the river, is B times sine of angle A, and then all of that divided by sine of angle B. Okay, all of this works really well, except we don't know what angle B is. We need angle B in order to figure out the value of angle A. Well, we can find angle B really quickly. Remember, angle B is just going to be 180 degrees minus the other two given angles. A and C are given. So you can see that angle B will just be equal to 180 degrees minus angle A minus angle C, which happens to be 34 degrees. So I'm going to use that value here. Let me just kind of separate this from our work over there. Okay, so then we can find that A is 75.6 feet times sine of 28.8 degrees, and then all of that divided by sine of 34 degrees. Cool? Let me move this up a little bit. So A is equal to, A is equal to, now when you punch all of this into your calculator, remember to use 3 significant digits. That's how many I count. And then I am finding that A is equal to 65.1 feet. 65.1 feet. Don't forget units, okay? This is the distance across the river. Okay, guys, here we go. Example 3. The bearing of a lighthouse from a ship was found to be north 52 degrees west. After the ship sailed 5.8 kilometers due south, the new bearing was north 23 degrees west. Find the distance to the nearest 10th kilometer between the ship and the lighthouse at each location. Okay, I don't know how you feel, but I feel like this would be a lot, maybe easier, reasonable to tackle, and maybe to even understand if we just draw a picture. So let's do that. And don't mind my sketch, okay? I'm not good at drawing lighthouses and a ship and all that. So I'm just gonna make it very, very simple, a simple drawing. Okay, you guys, this is what I've drawn. Here's the lighthouse. The bearing of the lighthouse from the ship's first location, all right? From the ship's first location is 52 degrees due northwest, okay? Then the ship traveled 5.8 kilometers due south, okay? This is due south. And the new bearing from the ship's second location was 23 degrees due northwest, okay? All right, cool. I've updated my picture just a little bit with due south here and 5.8 kilometers. Okay, the question is, find the distance to the nearest 10th kilometer between the ship and the lighthouse at each location. So I want to find this distance here, and I want to find this distance here. Okay, I think the first thing I want to do, now remember, this is 52 degrees and this is 23 degrees, okay? 52 degrees and 23 degrees. Now you can see then that this angle here will be the supplement of 52 degrees. Can I draw that in for you here? This angle here will be the supplement of 52 degrees. The supplement of 52 degrees is 128 degrees. So that's what that is, okay? That's 128 degrees. So then you can see in this oblique triangle, we have 23 degrees, the angle of that, the measure of that angle. We have 128 degrees, which is the measure of this angle here. The only angle that I do not know is this angle up here, but we can easily find it by using the fact that the sum of 3 angles of any triangle is 180 degrees. So this angle here will be 180 degrees minus 128 degrees minus 23 degrees. All right, so we found that this angle here is 29 degrees. Okay, everybody, 52 degrees was given. 23 degrees was given, which was one of the angles within the triangle. We derived both 128 and 29 degrees. All right. Now you know the angle measures within this triangle. Can we use the law of sines? So we can definitely use the law of sines. Notice that what we're looking for. We're looking for this distance, which I'm calling x here. The distance from the ship's second location to the lighthouse. And also we're looking for this distance here, which I called y, the ship's first location to the lighthouse. Let's focus on x first. I don't know, just because. I can use the law of sines as follows. X is to sine of the angle opposite side x, which is 128 degrees. Let's see, let's use another side length. The side length that you know is 5.8 kilometers. 5.8 kilometers is to sine of the angle that's opposite that side length, which is 29 degrees. Okay, so let's solve this for x. I'll move that up just a little bit. So then you're going to find that x is equal to 5.8 kilometers times sine of 128 degrees, and then all of that divided by sine of 29 degrees. Of course, punch all this into your calculator, and you're going to find also you have 2 significant digits, so that's how many significant digits you want here. And you're going to find that the distance from the ship's second location to the lighthouse is 9.4 kilometers. Okay, so there's one answer. That's the distance there for x. Let's do the same thing for y now. Now, when I set up y, the law of sines, that is for y, I'm going to put y over sine of the angle that's opposite side y, which is 23 degrees. And I'm going to use 5.8 again, kilometers, that's side length, over sine of angle 29 degrees. Okay? So we're going to find that y is exactly equal to 5.8 kilometers times sine of 23 degrees, all of that divided by sine of 29 degrees. And you're going to find that the distance from the ship's first location to the lighthouse to the nearest 10th kilometer is going to be 4.7 kilometers. So I'm hoping that you're finding these two answers. Okay, guys, let's push forward. The next objective, which within this section, we're already almost done, is deriving a brand new formula for the area of a triangle. So watch this. So to get this started, first of all, I say a new formula because we already have one formula, right? The area is equal to 1/2 times the base times the height. But you can see that in order for you to find the area of a triangle using the traditional formula, you need to know the base and the height. I'm going to show you a new formula where you do not need the height of the triangle in order to find the area of the triangle. I've started with that same oblique triangle that I had earlier, triangle ABC, and just like before, I dropped the perpendicular from vertex B down to side AC. Where this perpendicular meets side AC, I call that D, and this is now a right angle right there. All right, I want you to look at right triangle ADB, and I want you to notice that sine of angle A is equal to H over C, okay? H over C. That would imply that H is equal to C times sine of angle A. Now, our traditional formula for the area of a triangle is 1/2 times the base. Well, that's a little sloppy. Can I rewrite that 2 there? 1/2 times the base times the height. But now we can substitute the height of the triangle because we know that the height of the triangle is the same thing as the product of side C and sine of angle A. So I'll make that substitution right there. And we have that the area of a triangle is 1/2 times the product of sides B and C and sine of the angle that is included within those two sides. Look at angle A. Angle A is included within the sides B and C. Here's angle A, and here's side B, right? Side B as in boy, right? Not D, but side B and side C. Angle A is included within the sides B and C. So basically, this brand new formula says that the area of a triangle is equal to the product of 1/2 of the product of two sides and sine of the angle that's included. In other words, we can rewrite this formula. Can I move this up a little bit? You can rewrite this formula to mean the area of a triangle is 1/2 times the product of these two sides and sine of the angle that's included within sides A and C. The angle that's included within sides A and C is angle B. You guys get that? Or you can also write it as the area is equal to 1/2 times the product of sides A and B times sine of the angle that's included within sides A and B. Okay, so these three alternative forms here gives us a brand new formula for the area of a triangle, and it is not dependent upon the height of the triangle. This formula, all you need are two side lengths and the angle that is included within those two sides. And then you could figure out the area of the triangle. I mean, this is amazing. All right, cool. Okay, guys, look at this problem. Find the area of triangle DEF in the figure. The area of this triangle is what they're asking you for, and they're giving you the side lengths 9.0 feet and 12 feet. Notice you have two significant digits and 127 degrees. Hey guys, look at this. I figured out how to do the degree unit there, the unit for degrees. All right, cool. So anyway, that made me pretty excited there. All right, so what I want to do is find the area of this triangle. The area of this triangle is going to be equal to 1/2 times the product of the two sides times sine of the angle that's within the two sides, included within the two sides. So this is the work that I have to do. 9 times 12 is 108. Half of 108 is 54. So then this is going to be 54 squared feet times sine of 127 degrees. Okay, so rounded to the nearest square foot is going to be 43 squared feet. Don't forget squared, okay? Squared footage, because we're finding the area of the triangle. Isn't that pretty cool, you guys? Awesome. All right, find the area of triangle ABC if angle B is 58 degrees and 10 minutes, side A is 32.5 centimeters, and angle C is 73 degrees and 30 minutes. Now, in order for us to use the formula for the area of a triangle that we just derived, we need two sides. And so they only gave us one side here. So in order to use the formula, we're going to have to find either side B or side C. Either side B or side C. Either one of the two missing sides. If we solve for, I don't know, side B, then we're going to go B is to sine of angle B, what A there it is to sine of angle A. Okay, this is good and all, except there's an unknown in here. I mean, other than side B, of course, is what we're trying to find. And that is angle A. We don't know what angle A is, but we can figure that out pretty easily, right, everybody? We can find that angle A is just going to be 180 degrees minus angle B minus angle C. So we're going to find that angle A is, now let me rewrite 180 degrees actually, let me erase, can I erase this really quickly? And actually, let me do this in steps, just make sure that we're all on the same page. 180 degrees is the same thing as 179 degrees, is it not? And 60 minutes. That's 180 degrees. And I'm going to subtract angle B, which is 58 degrees and 10 minutes. We did this in the very beginning of our class. So this is going to be 50 minutes and 121 degrees. So far, this is 180 degrees minus B. Now I'm going to subtract C, which is 73 degrees and 30 minutes. So this is 20 minutes. 20 minutes and 121 minus 73, which is 48 degrees. So this is what A is equal to. So I'm going to use that in this law of sines in order for me to find side B. All right, everybody? So here I go. Side B over here, when I multiply both sides by sine of angle B, I get A times sine of angle B over sine of angle A. Does that make sense? So then A is 32.5 centimeters. That's given to me. Sine of angle B is 58 degrees and 10 minutes. All of that divided by sine of angle A, which I now know is 48 degrees and 20 minutes. Okay, guys, when you punch all this into the calculator, remember, if you wanted to use decimal degrees, all you got to do is divide 10 by 60, and that'll give you the decimal portion, okay? Or divide 20 by 60, and that'll give you the decimal portion for this degree measure, this angle measure. Okay, but my calculator, my scientific calculator, allows me to input degrees and minutes straight into my calculator, and then I can figure out what that is. Okay, guys, I punched it all into my calculator. You can obviously see that I did not round. I want to leave this number on my calculator just because it's not my final answer. So this is an approximation, so I want to use that calculator value. All right, and so when I move this up here, when I am now ready to find the area of this triangle. The area of this triangle is going to be 1/2 times the given side length. What's the given side length? Look at your given information. You can see the given side length is side A, and then you and I just found side B, and times sine of the angle that is included within the two sides. So then the area is going to be equal to 1/2 times, now side A was given to you, it's 32.5 centimeters, okay, times B, which is this long decimal. I'm not going to even write it all. I'm just going to do ... okay, etc. It's right up here still on the screen. That's what B is. Times sine of angle C. Angle C, what was it? 73 degrees and 30 minutes. 73 degrees. Let's see if I can fit this in here, folks. And 30 minutes. That looks a little strange. Okay, so I'm going to punch all of this into my calculator. Don't forget that 73 degrees and 30 minutes is the same thing as 73.5 degrees, because 30 minutes is half of 1 degree. So 73.5 degrees if you'd like. And we're going to round to the nearest square centimeters. We're going to round to three significant digits. Cool. What'd you guys get? I got approximately equal to 576. We're finding area, so this is squared centimeters. All right, I rounded to 3 significant digits. All right, you guys, that's what I got. This problem was cool. I used our brand new formula for the area of a triangle, but there was a few things I needed to find first, right? I needed to find that third angle that was not given to me, and I needed to find an additional side length. So I used the law of sines for that. All right, you guys, remember not to don't round your answers until you reach your final answer, okay? So don't round anything until you get to the end. All right, guys, this is the completion of Chapter 7, Section 1 on oblique triangles and the law of sines. I'll catch you in the next video, which is entitled 7.2, the ambiguous case of the law of sines.